Here we are, the last question except for the challenge ones, but Stats and Mechanics, Year 1, Chapter 11, Question 13, Variable Acceleration. At a time t seconds after launch, the space shuttle can be modelled as a particle moving in a straight line with an acceleration of a given by, they are some horrendous numbers, a equals, strap in for this, 6.77 times 10 to the minus 7 t cubed minus 3.98 times 10 to the minus 4 t squared plus 0.105 t plus 0.859, and this is for the realm of 124, so about 2 minutes. Is it in t seconds yet? 2.446. Okay, so about 2 minutes, and what's the other one? About 7 minutes. Okay, I wonder how accurate these numbers are. Right then. Suggest 2 reasons why the space shuttle might experience variable acceleration during its launch phase. Any suggestions, people? Okay, so the shuttle will have variable acceleration because the atmosphere has different densities at different altitudes. It will also have different mass as the rocket fuel is burnt. It may also lose mass due to separation of rocket modules. How's that seem? Okay. Right then. Given that the velocity of the space shuttle at time equals t, so at t equals 124, which is when this model starts, the velocity is equal to 974 meters a second, which is quite quick. Find an expression for the velocity of the space shuttle at time t given your coefficients to 3 significant figures. Okay, well, considering acceleration, not acceleration, but velocity is equal to the integral of acceleration by time, we just need to do the integral of that. So we will be increasing the power and dividing by the new power. So we will have, let's just go straight into it and write in as 6.77. Yeah, right. So we are going to have 6.77. Give myself some space here. 6.77 divided by 4 times 10 to the minus 7 t to the 4 minus, this is t squared, so this will be divided by 3, 3.98 dividing by 3 times 10 to the minus 4 t3 plus 0.105 divided by 2t squared plus 0.859t plus c. Okay, and we now know that the velocity is 974. So we know 974 exists, and we are putting in t to the power t to 124. So we need to put in 6.77. What's 6.77 divided by 4 is 1.6925. 6925 times 10 to the minus 7 times 124 to the power 4 minus 3.98 divided by 3, 1.3266 minus 1.32666 recurring times 10 to the minus 4, 124 cubed plus 0.105 divided by 2, which is 0.0525, 124 squared plus 0.859, running out of room, 124 plus c. And now, if we put all of that in and take it away from 974, we should get c. So, a horrible thing. Okay, 974 minus big bracket 1.6925 times 10 to the power minus 7 times 124 to the power 4 minus 1.326666 times 10 to the power minus 4 times 124 to the power 3 plus 0.0525 times 124 squared plus 0.0859 times 124. And now when you look back at your calculator, you realize on one of your powers you didn't move your button to the right, and so have made a heinous mistake on your calculator. I wonder if the calculator would be able to work it out. All the way back on my first power 4. Can I do anything about that? In terms of no, I can't. All I can do is (124) to the power 4 minus 1.3 . 4. Help if you knew how to use a calculator, of course. Minus 4 times 124 to the power. Power 3. 2 plus. Okay. I think that comes out as 369.0394 equals C, and so velocity is equal to, what were we doing? Find an expression for velocity, give your coefficients to 3 significant figures. .69 times 10 to the minus 7 t to the 4 minus 1.33 times 10 to the minus 4 t cubed. I wonder if they want them worked out. Plus 0.0525 t squared plus 0.859 t plus 369. Okay, I haven't looked at the answers just because it was so horrendous and I messed up with my calculator. That comes out as 273.175, which of course changes it just slightly, of being the 273. I think that's what it said. So now we can look at the next part of the question. They've got 274 in their calculations. Not sure where they've ended up with 4 from. I wonder if they have done rounding all the way through to 3 or 4 significant places, whereas I have not. But everything else I have written is lining up with what they've got, so the actual differentiation is, or the integration is correct. So I'm going to leave it at that. Okay. Right then, let's have a look to see what the next bit is. Find an expression, yeah, did that. Hence find the velocity of the space shuttle at t equals 446. So when t equals 446, we have to put this in. 1 moment. Well, I can't lie, I'm hating this question as one of the last ones in the book. Let's have a look then. When the time is 446 instead, we can come down here and we can put 446 in. So just adjusting the calculator from the last 1, 446. Should have really put it in with x's and stored the value, but and this one was it 169? Why is that 169? I feel like that should be a oh yeah, 169. Okay. 677 over 4. Okay, there's all of that, plus the 273. Let's just get that into the calculator. Plus 273, and I feel like this is going to be wrong, but anyway. So the velocity equals 6.698 times 10 to the power 10. What does it want it? To 3 significant figures. So velocity equals 6.70 times 10 to the 10. 59. Now something's not right with what I've put into my calculator then. Alright, I will go back to that and have a quick look. Okay, well, when I put it in again, it still doesn't give me the right answer. Incidentally, I've just looked at the answers, and in the answers, they give you 274 here, but in the worked examples, they give 273, which is not helpful. Then when they work this one out, they don't really mess around with it, but I don't get that anymore. I've just done it, storing it all as X, and I get, that was obviously wrong, 6,026. Okay, now 0.288. Now I am using no rounding at all, meters a second. Now they have got their answer down as 5,990 meters a second, which with 3 significant figures going on, I believe you could probably get as an answer quite happily in there. Maybe I should run it again without with the rounding done. Okay. Go do that. Right then, having just gone through it again and put in with the rounding all the significant figures, but using my 273 value, not their 274 in the one, I have come out with 5,986.8 meters a second minus 1, which does, when rounding to 3 significant figures, give you 5,990. This is a rubbish question, but that's only my opinion, so doesn't count for a lot. Right then, hence from t equals, the space shuttle maintains a constant acceleration until it reaches its escape velocity. It then cuts the main engines. Calculate the time at which the space shuttle cuts its main engines. So that sounds like a SUVAT problem. So let's have a quick look at what we've got. SUVAT, because it's constant acceleration, we don't know that. The initial speed was 5,990. The final velocity was 7.85 kilometers a second. So this is meters a second. So we need to do some conversions there. The acceleration is constant. Calculate the time, and the time is what I want to know. Okay. Oh, constant acceleration of 28. I do know it. 28.6 meters a second minus 1. Okay, so if we're doing 7.85 kilometers, we are doing 7,850 meters a second. Okay, by the time we finish that up. All right, where are the SUVAT equations? So we are looking for time, we're looking for the one with no S in it. Okay, and that is going to be V equals U plus AT. So we've got 7,850 equals 5990 plus 28.6 times t. So 7850 minus 5990, 1860. So we've got 1860 divided by 28.6 divided by 28.6 gives us 65.034 seconds. That's how long it takes, but we need to do that plus the 446 seconds because that's how far it is, plus 446 means it calculate the time at which the space shuttle cuts its main engines. So depending on where, 65 seconds after it does that, or from the time of launch, it is, oh, what's going on there, 511. It's 511 seconds. Okay, for the final part of that should be 510, two significant figures after launch. Okay. Ah, what a rubbish last question of year one. Right, no problem. Let's see if the challenge question's any better.